Now I'd like to say more about these three equations. And I'd like to start by continuing the discussion about the use of the Doppler redshift. So as we saw earlier, when the Doppler redshift, when people say they're using the Doppler redshift now, they're actually using a form of the cosmologic redshift, and they're using the distance dl in that form to solve in this way. Properly speaking, the Doppler redshift formula can only really be used if V1 is known and D1 is known. But neither one of those are known at the present time, so it's not practically possible to use the Doppler redshift formula. But it still might theoretically be the correct formula to use if it turned out that the universe operated in a particular way. And that way would be, suppose there was no stretching of light during the time that the light was traveling. In other words, that packets of light operated like little meter sticks and their wavelength did not expand as space was expanding. Then, since we obviously do have an observed redshift, the only explanation for the redshift that we know of at the present time would have to be that it's caused by a Doppler redshift. Now, in that case, we could calculate V1 by the simple Doppler redshift formula, but that would still leave us with a problem in calculating H because we wouldn't know the value for D1. Now anyone who wants to could work on that problem, but I'm not going to because I consider that to be a low probability scenario at the present time. The next thing I'd like to point out about all three of these formulas has to do with the timing. And that is to say that the stretching of light occurs during the time that light is in transit. The Doppler redshift occurs as a result of the relative recessional velocities at time equals 0. In other words, at the instantaneous moment that light is emitted. And the first principles formula takes both of those times into account in the way that the formula is constructed. Now, it's immediately evident that each of these formulas will result in different values, different calculated values for H. And one question which arises is which of the calculations will give the best value for H. Now this question, like all other similar questions in physics, will have to be determined by comparing the calculated values of H with other observed data in the physical universe to find which of the formulas is making the best predictions about how the actual physical universe operates. But some preliminary comments about that can be made. If it turns out that the Doppler redshift formula gives the best predicted values for H, then that would mean that there is no cosmological redshift and there is no stretching of light during travel, even though space is expanding. If it turns out that the value of H calculated using the cosmological redshift formula gives the best fit with other observed data, that would mean that there is stretching of light during travel, but there is no Doppler redshift component, meaning that the galaxy has no recessional velocity relative to the Earth, but rather is being held at a constant relative distance by some gravitational forces or by some other forces which have so far yet to be discovered or labeled. And if it turns out that the first principles formula gives the best fit value for h, that would mean that there is a stretching of light during travel which caused the cosmological redshift component, and there is a recessional velocity of the galaxy causing the Doppler redshift component in the formula. And one final comment can be made in introducing these formulas, which is that it's going to turn out that the value of h derived by first principles will be approximately equal to the value of h derived by either of those other methods divided by 2, or in other words, 1/2 of those other values of h. So if the value of h derived, let's say by the cosmologic redshift formula, is 76, the value of h derived for using the first principles formula will be about 38, and that would be for the same observed redshift and the same distance the light has traveled, dl. A little bit more precisely, we'll see that the values of h from first principles will mostly lie in this range of h, 1/2 of h, as calculated by the cosmologic redshift formula, and 1/1.h times h, with most of the values being closer to that end of this range.